Yeah, so let me write it down. Write down this result here. Today this is 16 December. So your homework was the following theorem. Irreducible aperiodic. So let me change this scale, then it works better. Irreducible periodic Markov chain is ergodic, exponentially ergodic. Is exponentially ergodic. What is irreducible? I recall that this means that it has the unique communicating class, right? A periodic, it means that the period of all states equals to 1. So the natural question which arises, well, and what is going on with periodic Markov chains? By periodic, I mean that the period is more than 1. Yeah, also I recall you that the period of all states of an irreducible Markov chain is the same. So I've proven this the last time. And concerning the periodic Markov chains, we have actually the following theorem. I will not prove it, but it's quite intuitive theorem without proof. It isn't so complicated. It's some quite simple number theory, elementary number theory, I would say, like that you had to use in your homework, but just to economize the time, I will not prove it. Okay, let's consider an irreducible Markov chain with period d. So all its states have some period d, which is, say, more than one. Then we can there is a unique partition of the state space. So this is a set of all possible states, usually denoted by X, to disjoint subsets X equals to disjoint union from J equal to say from 1 to D of some sets which I'll call Cj, such that, yeah, I recall that we are talking only about finite Markov chains. So the size of the state space is finite. So Cg are such that if the probability of transition between two states is strictly positive, so the probability to pass from the state I to the state J is non-zero. This happens if and only if I belongs to some CK and J belongs to the next subset CK plus 1. And here I denote I have D sets, right? So in such notation, I should explain what is CD plus 1, and I just denote by CD plus 1 C1, right? So this is a cycle, and this should be held for some K. For some K, where CD plus 1, this is the same as C1.
So K depends on I and J, right?
Yeah, sure. So the structure of the chain is as follows. You have your subsets of states, C3, etc., CD, and if you are here, then you can pass only here. If you are here, then you can go only here. If you are here, etc. And from here you can go only to the first set, C1. So let's consider some examples. So the simplest example, when you have, say, 3 states, and you have a chain like that. So what is the period of states? The period of states here is 3, right? And each class C1, C2, C3, this is just it will consist only of one state. So let us look at some more complicated example. The previous time we considered such a chain, and we found that the period of each state is 2. So we should be able to represent all states from 1 to 5 as a union of C1 as the joint union of C1 with C2, such that the property mentioned in the theorem holds. So it means that from C1 I can go only to C2, and from C2 I can go only to C1. So let us assume that the state number 5 belongs to C1. Then this guy, it should belong to C2. Then look, it's okay that I go from this to this because I go then from C2 to C1, but then I also can go from 1 to 2. It means that this guy belongs to C2. Then this guy belongs to C1. This is C2. Something goes wrong, right? Because
from 1 to 2 is wrong. The second one is C1 as well.
The second one,
second vertex.
Second vertex. Yeah, thank you. So this is C1 indeed. Yeah. This is C1. This is C2. C1, C2. Yeah, perfect. So you see this indeed works. C1. So this will be this C1 will consist of 2, 4, 5 of the states 2, 4, and 5, and the set C2, it consists of the remaining states 1 and 3. 1 and 3. You see? And you see, you have indeed some periodic structure in these chains with period more than 1. So indeed, the word periodic is the word periodic. This is a good word to describe these chains. So in particular, corollary. If an irreducible Markov chain is not aperiodic, so it has period more than 1, then it cannot be ergodic. It cannot be ergodic. Why? Why? This is a question for you.
Because we can take initial distribution, say 1 at the vertex 1.
Yeah. So for example, look, if you start with probability 1 from the class C1, right? So it means that we will arrive to the class in these steps. In these steps, we will arrive again to the class C1 for sure, right? And if you start from the class C2, in these steps, we will arrive to the class C2, right? So no mixing. So mixing is not impossible. So sorry, mixing is impossible because I mean ergodicity. Sorry, ergodicity is impossible because if the chain is ergodic, then you should converge to the stationary state. But and the stationary state should not depend on the initial conditions. But here you have clear dependence on the initial conditions, and it doesn't depend if the time is large or not. You see. So finally, we have the following corollary. An irreducible Markov chain is ergodic if and only if it is aperiodic. Okay. Because we have proven before, this was your homework, that an aperiodic Markov chain is ergodic. Irreducible aperiodic Markov chain is ergodic. So for irreducible Markov chains, now we have criterion. And the question is, what is going on with the chains which are not irreducible? In fact, here it makes sense also to mention that these chains are not just ergodic, but exponentially ergodic. The chain is exponentially ergodic because we have proven that a periodic chain is exponentially ergodic, right? Because we just used for the proof the ergodic theorem where we prove that the chain is exponentially ergodic. Well, but before passing to reducible Markov chains, let us ask the following question. But maybe, well, we see that the periodic chains, they cannot be ergodic, but maybe their stationary state is unique, or is it possible that an irreducible Markov chain, which is periodic, have more than one stationary state? How do you think? So is it possible that an irreducible Markov chain has more than one stationary state? So clearly, if it is aperiodic, then no, right? Because of the corollary above, because it is mixing. But if it is periodic, in fact, the answer is also no. So this is like lemma or theorem as you wish. No. So that is any irreducible Markov chain has a unique stationary state. So remember, before we have proven that any Markov chain with finite number of states has a stationary state, but we had many examples when the stationary state is not unique. The only situation where we knew that the stationary state is unique this was the case of ergodic Markov chains, right? But here we have something new. Here we have the situation when the chain can be not ergodic, right? When it is periodic, but I still claim that the chain has a unique stationary state. So I will not prove this lemma. I will give only the idea of the proof. In fact, this idea can be developed directly to the proof. So if you wish, you can do this as an exercise. Look, let us consider, let us do the following. We have this structure of these blocks C1, C2, C3, etc. So we assume that the period of the chain is D, right? More than 1, because for the period 1, we know that the chain is ergodic, so it has a unique stationary state. So we have this structure that from the block C1 we can pass only to the block C2, etc. From the block CD we pass to the block C1. And now let us consider another Markov chain which is formed by these blocks. Okay, so in fact this can be done. The question is how to determine the transition probabilities between these blocks. But this is not so complicated. In fact, this can be done quite easily. Just think about this. So let us just look at the example above. Where is this? Yeah, this example. So in this example, I will have the Markov chain like that. So I pass with probability. Wow. So this is no. Sorry. I've mistaken. I said something stupid because I proposed you to consider such Markov chain, but such Markov chain clearly has transition probabilities 1, right? Right. So this stupid Markov chain. So no, this is not what I wanted to do. I wanted to do different thing. On the contrary, let us take only the block C1, and let us consider this C1 as a new state space, and let us consider the Markov chain obtained from the original one, from the original Markov chain if I consider the Markov chain not in 1 steps but in D steps. Because according to this structure, in D steps, I arrive from the state C1 to the state C1, right? So if I consider my initial Markov chain, I can restrict it on the set C1, right? And I obtain some new Markov chain. And in fact, this isn't so difficult to see, and this is very intuitive from the structure, that this Markov chain is aperiodic. Because if it is periodic, so if its period is more than 1, then the period of the initial chain would be more than 1. In fact, would be more than D. In fact, because in this case you would be able also to separate this C1 for C1, say, and C1 prime, C1 prime and C1 2 primes, such that from C1 prime you go to C1 2 primes. And here you arrive from CD, and then you go to C2. So if this chain is not aperiodic, then you would have such situation, and the period would be D plus 1, but not D. But you do not have this, right? You do not have this. That's why your chain is aperiodic. But if it is aperiodic, it has a unique stationary state because it's mixing, right? Because it's ergodic. So it has a unique stationary state. And now, how to make a stationary state for the full chain, for the full initial chain? You just take, but this is rather clear. You just take this stationary state for this smaller chain, and then like you spread it over all the chain. Because look, if you start from C1, then you should pass, as we know, to C2, etc. Yes, then to C3, etc. And then you pass to CD. And from CD, you return back to C1. Then, do you have any suggestion how you can spread this stationary state? This stationary state, let me call it pi C1 to all the chain. Do you have any ideas?
Don't we just concatenate this stationary states?
But then the sum of probabilities will be
yes. We need to normalize.
Yes, of course. This is just it. So you just look. You just take the here. You take instead of the stationary state P C1 over D. So you divide each component by D, and then you just use your dynamics. You make push forward along your dynamics. So, for example, from this state of this block C1, you go to that state. And if this was state I, let me denote this state by J. Then the stationary distribution of I, this was P I C1, and then I normalized it over D, right? And then to J, I assign the same stationary probability. Okay. And then I continue my dynamics like that. So in such a way, I spread this stationary state to roll the chain. And it's easy to see that it will stay stationary. Okay, so in such a way, I've constructed stationary state for the whole chain, but my question is different. My question is why the stationary state of the whole chain is unique. But just because you can make the backward procedure, just take any stationary state of your chain. Take any stationary state of your chain, and then if you consider the Markov chain in D steps, this will give you a Markov chain on C1. It means that and from this stationary state, which is a different one of my whole chain, you will get possibly another stationary state P C1 tilde. But since the stationary state of this new Markov chain is unique because it's ergodic, they should coincide, right? But then there is a unique possibility to extend this stationary state to the whole chain, and this is the procedure which I have described. Right? So this, in fact, is a unique way to extend my stationary state to the chain. Is it more or less clear? So of course, this isn't an accurate proof, but this is the idea which it's possible to develop to the proof.
Can you repeat the argument about aperiodicity of this new Markov chain? Why the reduced Markov chain is aperiodic?
I mean, if it is periodic, it means that the period of the initial Markov chain would be larger than D. If it is periodic, then you can. I mean, if it is periodic, it means that this set of states C1, it can be divided by the theorem above. It can be divided to two states, C1 prime and C1 1 prime and C1 2 primes in such a way that from C1 prime you go to C1 2 primes, right? And from C1 2 primes you go back to C1 prime. But from
Okay,
this,
right.
you can in fact work out that the period of the initial chain would be larger than D. Okay. Okay, is it okay?
Yes.
Well, now we understand everything concerning stationary states of a reducible Markov chain. Let me repeat it. So once the chain is irreducible, it can be either periodic. So it has always unique stationary state, and it can be periodic or aperiodic. If it is aperiodic, then it is exponentially ergodic. If it is not, if it is periodic, then it is not ergodic. But from the periodic chain, we can construct an exponentially ergodic Markov chain, which is a periodic, by the procedure I described above. If we consider the chain in D steps, where D is a period, right? So the last question I would like to study is what is if the Markov chain is reducible?
So we need all the minimal ones to be ergodic.
Could you repeat? I didn't catch.
So we need all the minimal communication classes ergodic. Is it enough?
And then what? And then what?
And then the whole reducible.
No.
No.
No. Let us think about. Let's think about. Let's consider some reducible Markov chain. Look. Let us consider a simple reducible Markov chain in 3 states. 1, 2, 3. Up like that, and then you stay here. Then you stay here. So from the state 1, I leave it immediately, and I arrive either to the state 2 and stay here forever, or the state to state 3 and stay here forever, right? So already we see that this Markov chain has not unique stationary state. Yeah, what are the communicating classes? This is one communicating class, this is another one, this is a third one. What is a set of minimal communicating, of sets which lie in minimal communicating classes? This is a set 2 and the set 3, right? But they belong to different communicating classes. So here I see that the stationary state is not unique. So which stationary states exist for this chain?
0, 1, 0.
0, 1, 0.
0, 0, 1.
So this let me call it pi 2 and pi 3. 0, 0, 1. Do we have these are stationary states? So in particular, the chain is not ergodic. But clearly every minimal communicating class is ergodic, right? Consists only of unique station of a unique state, right? So and the reason is clear because starting at the point 1 at the state 1, you can go either here or here, and then you'll have different life. One life will be always here, and another life will be always here. So no mixing, right? You have mixing after you have arrived to the minimal communicating class. Once you have arrived, yeah, here you'll have ergodicity, but you cannot guarantee that you'll arrive here. Maybe you'll arrive here. So okay, so these are 2 stationary states. Are there another stationary states?
Yes, any their combinations.
Yeah. So you take any convex, you take convex hull of the set of these 2 stationary states. So just take lambda pi 2 plus 1 minus lambda pi 3, right? Lambda is in between 0 and 1. And this will be also stationary state. because our dynamics is linear. What is nice actually, because what are we looking at all this course? We're looking at the dynamics of measures, right? Because these stationary states, these probability distributions, in fact, these are measures. And the dynamic we have, this is the measure at step n. To obtain the measure at step n+1, you obtain by multiplying this measure at step n to the right by the matrix pi. But this is linear, right? You have some complicated process, but at the level of measures, the dynamics is linear. And this is what's nice in the theory of stochastic processes, because once you can consider some very complicated nonlinear equation, right? And then, but when you are interested in in distribution of its solution, this is a measure, and on the space of measures, dynamics is always linear. But when it is linear, we can make a lot of things. And here, since it is linear, then any combination, any convex hull of stationary states is again stationary state, right? Because you should multiply it to the right by the matrix pi, and this will preserve this guy, and this will preserve this guy. So it will preserve this guy. Yeah, so, but here it's very simple to write down. This is just 0, lambda 1 minus lambda, right? All vector like that will be stationary state. So now it's quite easy to see what is going on in general situation. So in general situation, when the chain is not reducible, you have some communicating classes, maybe something like that. But then you have here in each communicating class, you have many states, but some of these communicating classes are minimal. Say this one, say this one, and say this one. This is minimal, this is minimal, and this is minimal. Then we have a result from the last time, have a lemma which states that where is this? Yeah, here is it. Which states that the probability that we aren't yet arrived at a minimal communicating class decays exponentially. So it means that with exponential rate, we are going to a minimal communicating class. So earlier or later.
But it is not a minimal communicating class. It is a union of them.
Yeah, but union of them consists of. I mean, you cannot go to at the same time to two different communicating classes, right?
Yes.
Because once you arrive to one of them, you stay there forever. So with some probability, you'll arrive here, and this will be quite fast. This will be exponentially fast. With some probability, you'll arrive there, and with some probability, you'll arrive there, right? And then when you are leaving, when you have already arrived to the minimal communicating class, then you have an irreducible Markov chain, essentially, right? And for irreducible Markov chains, we know everything. If it is aperiodic, then there inside of this minimal communicating class, you have ergodicity. If it is periodic, you do not have ergodicity, but you have the unique stationary state there, right? So finally, we have the following picture. So we now I'll write maybe not very in a very accurate way, but I think that it's clear what I mean. Exponentially fast. Okay, exponential conversions to a union to E, to the set E, which is a union of minimal communicating classes. In which sense? In the sense of lemma above. In the sense of, oh, sorry. in the sense of the lemma above. Then, if a class where you entered is aperiodic, then you have ergodicity inside of it, of this class. So, but if it is periodic, then no ergodicity. But a unique stationary measure. But a unique stationary measure inside of this class. So finally, we have the following theorem. Well, let me write it down accurately. Homogeneous with finite number of states, Markov chain is ergodic if and only if what? If and only if what? Who can tell? If and only if what happens? So first, how many minimum communicating classes should it have?
Just one.
Just one. If it has more, then maybe I'll enter here and I'll leave here, maybe here and maybe here, right? So no mixing. And moreover, if I start already in the minimal communicating class, then I will stay there forever. So if I start here, I stay here forever. If I start here, I stay here forever. So no mixing is possible. So if and only if it has a unique minimal communicating class,
And it is periodic. And it is a periodic.
yes, exactly, and it is aperiodic. And moreover, in this case, it is exponentially ergodic. So, in particular, we have understood that not exponential ergodicity is not possible for finite Markov chains. Once you are ergodic, you are automatically exponentially ergodic. Okay, so polynomial convergence is not possible. It's always fast. It's always exponential. Well, so
the aperiodic requirement is for minimal class, right? Just for the minimal class.
Yes, and it is aperiodic, so it means that minimal communicating class is a periodic.
No, but chain can chain be aperiodic?
But aperiodicity, I mean, period is defined only for given communicating class, right?
Okay. Right.
Moreover, for minimal communicating class, because
Yes.
period is defined only for irreducible chain, right? And only minimal communicating classes are irreducible, right? Because from all other classes, from all other communicating classes, you can leave them. For this class, the period is not defined because you leave it for this class or for this one, and then you leave it for this one. See? So in general, your life is as follows. You arrive to one of the irreducible, for one, or you arrive to one of minimal communicating classes, If it is unique, then perfect. You arrive there for sure. You arrive to this class exponentially fast, and then you start to live there. If this class is aperiodic, then you have ergodicity. Then you converge to the unique stationary measure. If this class is periodic, then you go over this period all the time according to the theorem we discussed today, right? If you wish to make from this periodic Markov chain which you obtain, if you wish to make an aperiodic one, you should consider a Markov chain in a number of steps which equals to the period of the chain, right? And also, if this will be theorem 1 and theorem 2. Theorem 2, a Markov chain. So here in brackets, this is the same homogeneous number of states is finite. A Markov chain has a unique stationary state. State if and only if what? It has a unique minimal communicating class. Look, this holds because if you have two minimal communicating classes, then exactly as in this example, your stationary state will not be unique. But if you have a unique minimal communicating class, say the structure of your chain is like that. You arrive there, then you arrive there, then you arrive there. So these are communicating classes, right? Inside of which class you have many states. If your chain is like that, then you have the unique minimal communicating class, and it means that you arrive here for sure. But then you start to live in an irreducible Markov chain, which is given by this minimal communicating class. And we know that for an irreducible Markov chain, the stationary state is unique. You see, moreover, the stationary state will have non-zero components only for states which are in this minimal communicating class. Okay, is it fine?
Yes.
So now, now you understand. We understand. So we have complete classification of limiting dynamics of finite Markov chains, right? There is another type of questions which can be asked for finite Markov chains, and this type of questions we have not discussed in our course. This is a question, well, let us consider a Markov chain which has more than one minimal communicating class, well, as in the picture. Then with which probability I will arrive to this communicating class, and with which probability I can arrive here? This, from the practical point of view, these are very interesting questions, because, I mean, like you have some machine which has two stationary states. In one stationary state, everything works well. In another stationary state, nothing works. And you are interested in with which probability you arrive to the good stationary state. But good station, this good stationary state, I mean, it is provided by some good minimal communicating class. You see. So if you are here, you goes well. If you are here, nothing works. You're interested in with which probability you will arrive here. So this is a very reasonable question. Another type of questions. So the next development of all this story, this is of course Markov chain with infinite number of states. Here there is some new effects. The new effect can be easily seen in the chain like that. Just you see, if you consider the chain which goes away to infinity and never returns, this is what cannot happen in finite Markov chains. So from this example, it is clear that some new assumptions, some new technique, maybe not new technique, but some new assumptions are needed in order to prove ergodicity. This is also a well-developed subject. Actually, this is, I mean, sometimes this is quite tricky, and this is interesting. And also, it was Kolmogorov who proved significant part of results there. But and then if it is Kolmogorov, then this means that this is non-trivial. I would say like that. So if you're interested in, you can find it just in any book. For example, in Shiryaev, this is the standard book. And here this classification, this periodicity, and so on, it's strongly used. But basic ergodic theorem for infinite number for chains with infinite number of states. It sounds in a similar way, but you have some additional assumptions that you do not have. That you do not have a situation like here, that you just go away to infinity. Okay, so this is the end of the course. Do you have any questions? No questions. Well, so then I'll write you this evening or maybe tomorrow about the exam. Okay, so bye.
До свидания.
Спасибо большое.
Не за что. Так, да.